In this video, we're going to be going over action potential generation and transmission. And actually, this video is the first in a two-part series where we're going to look at action potential generation in this video, and then the next video looks at action potential transmission. The steps involved in the generation of an action potential and its transmission are similar in both neurons and skeletal muscle cells. What I'm going to do in this video is I'm going to focus on how an upper motor neuron stimulates a lower motor neuron. Remember, an upper motor neuron, the cell body, is located up here in the primary motor area of the cerebral cortex, and the axon of this neuron comes down from the brain, down through the spinal cord, and then at the very end of the axon terminal, it synapses with the cell body of a lower motor neuron. And its axon goes out, and that's going to innervate a skeletal muscle. So I'm going to focus just right here, where the axon terminal, synaptic end bulb, synapses with the lower motor neuron cell body. And we're going to look at the development, the generation of action potentials here. And then their transmission will be along the axon. In step 1, an action potential or neural impulse moves down the upper motor neuron's axon to the synaptic end bulb. And this synaptic end bulb has been enlarged. That's what you'd see here. Well, this action potential is going to open up voltage-gated calcium channels. Remember, when you're talking about action potentials, it's sodium moving in through voltage-gated sodium channels and potassium moving out through voltage-gated potassium channels. Well, that sodium moving in is going to depolarize that membrane, positive 30 millivolts. And when it does that, that's the voltage that opens up voltage-gated calcium channels, and then calcium comes into the synaptic end bulb. Well, the rise in calcium triggers acetylcholine-containing synaptic vesicles to release the neurotransmitter acetylcholine into the synaptic cleft by the process of exocytosis. In your notes, you have this diagram here, and this is your upper motor neuron synapsing with the cell body of the lower motor neuron. Here's your action potential coming down. It's opening up voltage-gated calcium channels. Calcium moves in, which stimulates the release of synaptic vesicles containing acetylcholine to be released by exocytosis. That goes out into the synaptic cleft, diffuses across, and is going to bind to acetylcholine receptors, which are also known as ligand-gated sodium channels because these allow sodium to come through when the ligand, known as acetylcholine, binds to it. Well, the acetylcholine is going to diffuse across your synaptic cleft, binds to acetylcholine receptors on that postsynaptic membrane of the lower motor neuron. The binding of acetylcholine is going to open up these receptors, and sodium is going to flow through. And sodium flows down its electrochemical gradient, we say, which is a scientific way of saying that sodium flows down its concentration gradient. Because remember that sodium is higher outside the cell than inside. So when it opens up a channel, it wants to go down its concentration gradient. And so as sodium comes in through the neuron, it's coming down its chemical gradient. Well, sodium, which has a positive charge, is also attracted to the negative charge, minus 70 millivolts, that's the resting membrane potential, inside this cell. So that attraction is the electrical gradient. And so we say it moves down its electrochemical gradient. Well, as this sodium flows through these open channels, the voltage across this lower motor neuron membrane changes. And in this case, it depolarizes. It becomes less negative because you have positive charges coming in with sodium. Well, before we get to step number 7, it's important to note that acetylcholine is broken down by an enzyme called acetylcholine esterase. That way, when this upper motor neuron stops sending action potentials, stops release of acetylcholine from this neuron, that acetylcholine doesn't stay in the synaptic cleft and keep stimulating those acetylcholine receptors. So you have acetylcholine esterase, which is represented by these cup-like structures here. And that breaks down acetylcholine to an acetate group and the choline group. Thereby it stops activating the acetylcholine receptor. So far, the acetylcholine is bound to the acetylcholine receptor, which is, like I said, it's a ligand-gated sodium channel. Sodium comes in, and it's going to make the inside here of the membrane less negative. It starts to depolarize it here. If this depolarization reaches threshold, then it's going to trigger an action potential at the axon hillock, which moves down the axon of the lower motor neuron. threshold for a typical neuron is minus 60 millivolts. As this sodium comes in, it creates what we call a graded depolarization. The positive charges of sodium come in and causes this minus 70 millivolts, which is a resting membrane potential, to become less negative. If it reaches minus 60 millivolts, that's what we call threshold. And that is the voltage that opens up voltage-gated sodium channels, which are found right here at the axon hillock. They're found all the way down the axon, but that's where they begin. So we say that action potentials start at the axon hillock, but you've got to get that voltage-gated sodium channel to the voltage that it opens. And how do you get it to that voltage? It's the sodium that's coming through those ligand-gated sodium channels, those acetylcholine receptors, that brings it to threshold. And if it doesn't make it to threshold, let's say it makes it, instead of minus 60, it gets to minus 65 or minus 61, that's not going to bring it to threshold. It has to hit minus 60. And if you remove the stimulus, if you stop releasing acetylcholine, and it hasn't brought this to minus 60, then it'll just go back to its resting membrane potential and you won't fire an action potential. You want to make sure you note that graded potentials are short-lived local changes in the membrane potential. And that's what we find right here. This is a graded potential as sodium comes in. And we call it graded because its magnitude decreases with distance as the ions move in, the sodium, which we refer to as current, spreads along a stretch of the membrane. If I take the cell body here of this neuron and I bring it over here, these are the acetylcholine receptors. When acetylcholine binds, allows sodium to come in, and as that sodium comes in, it's going to change the resting membrane potential right here at the membrane from minus 70 to become less negative. Now we call this a graded potential, and its strength depends on how many ion channels are open and how many ions come through to form the graded potential. Now what's so special about this? Well, as these sodium ions are moving in, it's right next to the axon hillock, and if enough sodium comes in to bring this to threshold, it will open up voltage-gated sodium channels. That's how we get these voltage-gated sodium channels to open. It reaches threshold, minus 60. That opens up a voltage-gated sodium channel, sodium comes in, and then that sodium is going to diffuse from this channel, and this voltage-gated sodium channel is at minus 70 millivolts. Remember that resting membrane potential is all the way down the axon. And if you have enough sodium come in here to bring this to threshold, then that opens and then sodium comes in and can bring the next one to threshold. Now this is getting into transmission of the action potential. But for right now, you just need to know that this graded potential here is all about bringing the membrane to threshold to open up voltage-gated sodium channels, which are going to start the transmission of the action potential down that axon. When we have enough sodium coming in here with the graded potential, and it opens up this voltage-gated sodium channel, you've reached threshold, then we have an action potential starting. And an action potential, remember, is a movement of sodium in and a potassium out through these voltage-gated sodium and potassium channels respectively. And as that sodium moves in, we have what's called the depolarization phase. You want to make sure you star that. At threshold, voltage-gated sodium channels open and sodium moves into the neuron, going down its electrochemical gradient. Well, this influx of sodium causes the inner membrane surface to go from threshold to positive 30 millivolts. And it's classified as a depolarization phase. So that's that sharp upward spike of the action potential. Now watch this. This is really cool. As this sodium reaches positive 30 millivolts, that's the voltage that closes voltage-gated sodium channels and opens voltage-gated potassium channels. So once you hit positive 30 millivolts, the spike stops. You can't depolarize any further because the voltage-gated sodium channels are slammed shut and they become deactivated. They will not be activated to reopen again until after minus 70 millivolts, until after it passes that resting membrane potential. The channels that do open up right here at positive 30 millivolts, voltage-gated potassium channels. And potassium is going to leave out of that axon or that membrane. And then that leaving of positive charges is going to repolarize it, make it more negative again. And we call this the repolarization phase. The repolarization phase is where you have the opening of voltage-gated potassium channels and potassium leaves, those positive charges leave, which repolarize it. And that gives you the sharp downward spike of the action potential. Well, when it hits minus 70, that's when voltage-gated potassium channels close. But unlike the sodium channels that all slam shut at positive 30, you don't get a higher spike in the action potential because they've all slammed shut. Voltage-gated potassium channels don't all slam shut at the same time. Some slam shut, and then others will slam shut as it becomes more negative until you hit minus 80 millivolts, and then all of them are shut. And then it comes back up to resting membrane potential. Well, what do we call this phase when it drops below the resting membrane potential as voltage-gated potassium channels are closing? We refer to that as hyperpolarization. It goes more negative than the resting membrane potential. You want to make sure that you can trace out this action potential where you have a stimulus. This is bringing it to threshold, sodium coming in, raising it to threshold, and then a depolarization phase and a repolarization phase and a hyperpolarization phase and returning to resting membrane potential. The next video is going to go into the transmission of an action potential, because once you've started the action potential here at the axon hillock, how does it get transmitted along that membrane? That's going to be the topic of the next video.